Now for the second exercise, which is quite similar to the first one. Again, we have a 2 times 2 matrix here, and then afterwards another 3 times 3 matrix. But there are some differences as far as the solutions are concerned. Firstly, which you may know because this has already been done by Martin in the lecture. This is a matrix which, although it's a real, okay, it has only real numbered elements. It turns out that it has complex eigenvalues, 2 of the sort, and most interestingly, these 2 eigenvalues are even complex conjugates to each other. So this is not by chance, but and what it means geometrically speaking is that there is not even a single direction in the 2-dimensional vector space which remains unchanged by applying this matrix. But mathematically, if we allow for complex values, you could say that the formal prerequisites, the formal conditions for an eigenvalue to be valid and also a corresponding eigenvector are fulfilled. And this is what we will see, but no, we won't see it. I just tell you and jump over this shortly. But you may remember if you just do the usual approach and follow the usual approach and then get your characteristic equation, it turns out that the square of this parenthesis term in parentheses must be -1, and then you draw the square root, of course, by the methods of complex algebra or arithmetics, and you find easily that the resulting eigenvalues are 1 minus or plus, well, I could also say plus or minus j or I, however you call it, the imaginary unit. So now the interesting thing is if I test this, I have to put this in by subtracting it on the diagonal, and suddenly I get a matrix, of course, with complex entries. But this is also a part of the explanation that these complex values are valid because there are corresponding eigenvectors which also contain the imaginary unit, so that this one of these complex factors multiplied with this complex valued vector definitely produces a multiple of this vector. But all I'm saying is just valid inside the complex calculus, the complex algebra. Okay, you know what I mean? And just for testing it. So I put in this 1 minus j eigenvalue first, and then I get j on the diagonal, and then applying, well, solving this, you see that the j-fold, if I take this row times j, it transforms to -j here, but j times j is -1 here. And then so it's almost the same as the first row. It gets a 0 row. And if I read out the solution, I get j times x1 plus x2 equals 0. And then x2 equals -j times x1. So that's in the end, for example, the vector 1 minus j, it fulfills this equation. So now if you would test, this is the test, using this vector and applying our original A matrix to it, we would get 1 times 1 plus 1 times minus j, so 1 minus j for the first component, and for the second one, -1 minus j. And as you see, after a while, this is exactly the original vector multiplied by this complex eigenvector 1 minus j. So formally, everything is fine. We found a valid eigenvalue and corresponding eigenvector, but both of them are complex valued, which means this is the result which extends over the purely geometrical interpretation. Okay, so this cannot be interpreted with simple geometry anymore. Okay, so that's all I wanted to say about this. About the same holds for in analogy for the second solution. I wanted to have a short look at this because here we have an interesting case. It's quite, as you see, quite the same procedure as before, constructing this polynomial of lambda. Again, I would recommend Sarru's rule. I didn't even yes, put it here, but as you can see, this is the main diagonal product, 4 minus lambda times 1 minus lambda times negative lambda. You see that I multiply these two, which is 1 minus lambda times minus lambda, so negative lambda plus lambda squared, this one here, okay, and then times 4 minus lambda. So that would be this third order contribution from the main diagonal. But then you see, due to this 0 here, I get for the second for the next diagonal contribution, I get 2 times 0 times something, so it's 0, and then plus 3 times, and then jumping here, 2 times minus 2. 3 times 2 is 6, times minus 2 is negative 12. So that's how it comes along. Okay. Also, for the negative counting contributions, we have 3 times this 1 minus lambda, which is 3 minus 3 lambda. If I multiply these, 3 minus 3 lambda, and times negative 1 times minus before from the scheme. So again, it's minus 1, which is neutral then, factor of 1, and then we just have to multiply 3 times 1 minus lambda, which is 3 minus 3 lambda. So that's why I shortened this. Then I get a 0 contribution for this parallel. Am I right? Yes. This counts negative, this counts negative, and the last one would be this times this times this. So it's negative lambda jumping here times 2 times 2. So minus 4 times minus lambda, which is plus 4 lambda. So it's quite easy due to the 0 contributions. It's a little quicker to solve than the first one. Anyway, you see negative lambda to the power of 3 again, the strongest term here. Then also some quadratic contribution, altogether 5 lambda squared. Well, where does it come from? Look here, 4 times lambda squared. Let me see. Okay, take care, because we also have minus lambda times minus lambda. So this is 1 lambda squared plus another 4 lambda squared, which is 5 lambda squared, and that's it. Okay, and for the linear contributions, negative 3 times lambda plus 4 times lambda, which is positive. What is it? Am I right here? It's really of course also I must take care. Here I have 4 times negative lambda, so that's minus 4 times lambda from here, and then minus 3 times lambda, which is minus 7 times lambda, and then plus 4 times lambda, remaining is negative 3 times lambda. So that's correct. Okay, and then also we have negative 12 plus 3, which is negative 9. So in the end, you can guess the minus 1 as a solution. You just put it in, and then you get, in the end, you get minus times minus is plus. You get 1 here, 1 plus 5, yeah, squaring takes away the minus sign. So 1 plus 5 is 6, minus 3 times minus 1, 6 plus 3 is 9, minus 9 is 0. So it's this is easy to guess. And then, I use the chance, and I don't know if you're not familiar with the Horner scheme, don't care about it. But if you know it, it's quite nice, because it's a very quick method for polynomial division of a linear factor. So if I want to divide this lambda plus 1 linear factor, which corresponds to this solution, out of this polynomial, it's quite easy to do. I just take the coefficients, minus 1, 5, minus 3, minus 9. Then I write here lambda equals minus 1. This I always use the solution to which I want to, well, it's if I want to divide this linear factor out of this polynomial, I put the corresponding solution of the characteristic equation, which is minus 1, here. And then I draw a horizontal line, and then there is a certain procedure, which is easy to derive, but we don't have the time now. You can do a classical polynomial division also. So then I take the first element downwards, minus 1. I multiply it with this number, always. Always the next step is multiplying with this number here. So minus 1 times minus 1 is 1. I put this here. one to the right and one upwards. Then I add the column numbers, 1 plus 5 equals 6, and then the same procedure again. 6 times -1 is -6, -6 minus 3 is -9, -9 times -1 is 9, 9 minus 9 is 0, and if I get my 0 here, this is the test which states that everything works fine, or worked fine, because there is no rest. This was a division with rest 0. That's what I wanted, and this is the control 0, you could say. So, and then I can decode these numbers as to be the result of the division, which is -1 times lambda squared plus 6 times lambda minus 9 constant. It must be a polynomial of grade 2 because I divided a linear factor out of a cubic polynomial. So if you don't know the Horner scheme, don't mind. I don't care. Just use classical polynomial division. This was very short now. What I wanted to say, please check yourselves. You will find a double solution again, one double solution, which is 3 as an eigenvalue. It's an eigenvalue of algebraic multiplicity equal to 2 again. So we would expect an eigenplane again, as in the former example. But as I told you, it can happen, and in this case it will happen, that although this is a double solution, anyway, you will find just a single, or let's say a simple eigenspace, a one-dimensional eigenspace. In other words, an eigenline. It's just a fact that the algebraic attributes of a matrix may differ from its geometric attributes, you could say, in a certain way. So in the end, you will find just one eigenvector to this matrix. Oh no, sorry, we have, is it? Let me see, yeah. I forgot the guessed solution, which is -1. Okay, we have this eigenvalue. This, of course, must have an eigenline to it, but the other one, which could have an eigenplane, also has just an eigenline. That's what I wanted to say. So we find two different linearly independent eigenvectors for two different eigenvalues, but for the double solution of our characteristic equation, this one, algebraic multiplicity equals 2, we find also only one direction for the eigenvectors, which corresponds to a geometric multiplicity of 1. So that's the special case which I wanted you to have seen at least once. And as I said before, the optional exercise we will just ignore it because it's too far ahead. And this is, and I must say, it's a very interesting topic about quadratic forms and principal axis transformation, especially in data processing and etc. It's very useful, but it was not really part of what you learned in the lecture. So let's just leave it away. And next week, let's look at sequences and series. Thank you.